AP Chemistry lecture for oxidizing and reducing agents that we went over in class on Thursday and Friday. And this will be on your test, so you do want to make sure that you go over this. This PowerPoint is uploaded, so you can print off the PowerPoint and look on as I go through it. But you want to make sure maybe you either copy it or at least read it. So this is continuation of electrochemistry. We've talked about oxidizing and reducing agents before. Now we're going to relate those to voltage. The more positive the voltage, which we call reduction potential, which means its potential to be reduced, the more likely the substance is to be reduced. This is also going to make it a stronger oxidizing agent. The word that the book uses for oxidizing agent, they actually call it an oxidant. So basically they'll run those two words together, oxidizing agent and the word oxidant mean the same thing. So the more positive your voltage, the stronger the oxidant is, that would be the reactant, and it's more likely to be reduced. And then the opposite of that, the more negative the reduction potential, the more likely the substance is to be oxidized rather than be reduced. And this is going to be a stronger reducing agent, and the term that we sometimes use in the book is called a reductant. So there is a worksheet that goes with this, and those types of questions that are on the worksheet will be the types of questions you will see on your test. So what we did in class, the very next slide, has the chart that I gave you guys when you took your quiz, so you should have a copy of this. If not, you can print this off and you would have another copy of it. This is a reduction chart. You know it's a reduction chart because all the E's are over here on the left. They're all starting as ions and they're making solids. When we talked about the metals, we were talking about a few nonmetals, then they're starting out as element form and they're actually going to ion form. So because it's a reduction chart, everything's being reduced. And if you look, the highest voltage here is going to be the one that is most likely to be reduced. And the one that is most likely to be reduced on this chart is fluorine. Fluorine gas, it's right here, is most likely to be reduced. And the reason we know that, it has the highest voltage. So if I were to label him, kind of like if you were labeling somebody in class most likely to succeed, this guy is the most likely to be reduced. And that increases as we go up. It's not a very straight line, but as we go up, this one is so much more likely to be reduced than lithium. If you look, lithium is actually a negative here, so lithium ions don't like to be reduced to lithium solid. That's why we find lithium don't find lithium very often, not in ion form. He doesn't like to be in a solid form. So these are least likely to be reduced. So least likely down here, most likely up the top. Now if we think of this the way we're written, if this is being reduced, then this would be labeled as an oxidizing agent. So up here we would have the strongest oxidizing agent, also known as an oxidant. Down here we would have the weakest oxidizing agent. So if I ask who's the stronger oxidizing agent between copper 2 and zinc, well, he's up higher in the chart. He is a stronger oxidizing agent, copper 2 is. Then there's some questions on the worksheet about, well, is it weak or strong? And here's our division line. Our division line is right here at the hydrogen. All the guys that are negative are actually weak oxidizing agents. All the guys that are positive are actually strong oxidizing agents, or actually strong oxidants or weak oxidants. So that's how you know, depending on if they're negative here or they're positive. So hopefully that makes sense to you as far as most likely to be reduced, or strong as oxidizing agent, or weak as oxidizing agent. Now we're going to get a little confusing because when I used to teach this and I had my overhead projector, I could actually take this transparency, because I had this little thing on a transparency, and I could flip it over. And when I flip it over, they're no longer reducing equations are actually oxidizing equations. And so if you flip it, so now we would have this guy written over here and these guys written over here. When you do that, all your charges actually become negative up here and positive down here. So now you have to think in flip mode, because unfortunately they don't make an oxidizing chart. They expect you just to be able to read this chart as an oxidizing chart. So now if we think of it as flipped, a flipped chart, I'm going to write flipped up here. Okay, when flipped, these guys would all be negative, and these guys would now be over on the reactant side, these would be on the product, and these would be oxidized. So therefore, since these are going to be negative, these are going to be the least likely to be oxidized. And down here, if we were to flip those, we're talking about lithium as our reactant, that would be most likely. My pen is not working very well because I'm sitting so close to the Bluetooth. Most likely to be oxidized. So now, again, we're still thinking of them as flipped. If they're flipped, if it's going to be oxidized, this would actually be a strong reducing agent. So our strongest reducing agent is actually lithium solid, and the strength increases as we go down. Again, not a straight line. Sorry about that. So the type of questions that are on the worksheet would be something like this. If I gave you Cl2, and I said, is Cl2 a strong oxidant, weak oxidant, a strong reducing agent, or a weak reducing agent? Well, since he's over here on this side, he's actually a strong oxidizing agent. And we got a knock on the door, so hold just a second. Okay, we are back. Sorry about that. So that would be the types of questions. So now if I gave you like silver solid and I asked the same questions, would it be a weak oxidant, strong oxidant, weak reduction agent, or a strong reduction agent? Well, since he's over here, and if we were to flip him around, he would actually be being oxidized, and he would be a weak reducing agent. So over here are going to be reducing agents if I give you one of those. Over here, if I give you one of those, they're going to be oxidizing agents. Up here are the strong oxidizing agents. Down here are the weak oxidizing agents. Over here are the strong reducing agents. Up here are the weak reducing agents. And if you can learn that, you can answer all the questions that would come on the test from that. So again, there is a worksheet. It is attached on Edmodo, or if you were absent, you can come by and get that from me. So don't wait till the last minute, because that is on the test. Our next thing is something called Gibbs free energy. Now we're actually going to learn more about Gibbs free energy later when we talk about thermodynamics and we talking about thermochemistry. But since we're talking about voltage, there is an equation that relates it to voltage, so we're going to go ahead and do Gibbs because it's kind of easy. And then later when we do thermochemistry again, I'll say, remember we did Gibbs with voltage, and then we'll come back and look at this equation again. So what you kind of need to know, if it's negative, free energy means that the reaction is going to be spontaneous, and that E's are related by the following equation. And here's our equation that we're going to be dealing with. Delta G stands for, delta means the change in, G means Gibbs free energy, then it's a negative, N is going to stand for the number of electrons that are going to be passed, F stands for Faraday's constant, and E is actually voltage, and that's actually on all the stuff is on the next slide. Again, you can print these slides off and you can have these, so this is what everything stands for. I'd like you to show you something. Do you see this right here? Gibbs is actually measured in kilojoules per mole, but unfortunately Faraday's constant is, and that is a time sign, so it's actually a joule/volt times a mole. It looks like that. When I multiply these numbers together, the unit actually comes out in joules per mole, And so you're going to have to divide by 1,000 in the end to make this work. I don't know why they don't just give the constant this way. We're just going to use this constant because that's the same one you're using with your electrolysis. So that way you can already remember this constant is 96,500. So we're going to work one of the problems. If you pull up the PowerPoint that I uploaded this PowerPoint yesterday, and I have changed the example problem. So to make it a little bit simpler, this will probably be one like you will have on your test. It says, what is the Gibbs free energy for a reaction of copper 2 nitrate with sodium metal? And wants to know if this reaction is spontaneous or not. Well, the first thing we would want to do would be write the equation. So you've got copper 2 nitrate, and we're reacting it with sodium metal. And we've got a single displacement reaction, so it definitely is a redox. Single displacements are redoxes. And so sodium is going to hook up with nitrate, and poor little copper is going to be left all by himself. It doesn't have a 2 with it because it's just a solid piece of copper. Now if you will do net onyx, it will make this a lot easier. Hopefully you can see we're going to slash this because we slash all nitrates. We slash them, we put their charges. Technically we label them aqueous. This is a piece of metal, so he gets boxed, no charge on him. He is a solid. This is aqueous because of that nitrate again, and this is a piece of metal labeled solid, no charges. So if we get rid of our spectators here, our spectator again is nitrate, my favorite. So we could say, well, we really got some copper ions reacting with some solid sodium. Going to make us some sodium ions, going to give us some solid copper. So there is our redox reaction. You can see copper going from a 2 to a 0, and sodium going from a 0 to a +1. So we're going to want to break this into half reactions and balance it. You could have balanced it up here, but I want to do half reactions because we need to see the electrons. And half reactions are where we see the electrons. So this guy is going to match up to this guy. We're going to put 2 E's over here on the reactant side. This is a oxidation or reduction. This is a reduction because my E's are over here on the reactant side. And then we've got sodium, going to go to sodium ions. And then we're going to have only 1 E here. Now, we want those E's to cancel out for the overall reaction. So in order to do that, we need to run a 2 through this equation. Now, if I rewrote this, you would actually see those E's canceling. It's going to be real important for that to happen. This is very much like your lab where you make those E's go away. Alright, so there's my equation. Now, we could actually look on the chart and find the voltage. And so if we looked on our chart for copper 2 going to copper solid, this actually makes a positive 34 volts. This is just like he is in the chart. This guy is flipped because he is being oxidized. So if we look on our chart, we will find on the chart it's a negative 2.7, so we flip him around, it's a positive 2.71 volts. And I'm simply going to add those together, and that's going to make 3.05 volts. So that's good. Is this spontaneous or not? It's spontaneous because we have a positive voltage. So you can actually tell if something's spontaneous or not by just looking at the voltage. But we're going to put him in Gibbs free energy just so we can see how that formula works. Delta G equals negative N times Faraday's constant times the voltage. The little circles just mean they're at normal standard conditions. We've got a negative. The N stands for the number of electrons. That's why we needed to have, it's not 4, it's 2. 2's giving and 2's taking. So it's a total, like if I were giving someone a quarter, I would give up a quarter and they would take the quarter. That wasn't 2 quarters, that's just 1 quarter. It's a give and a take. There is, so happens to be 2 here, so this is 2. Faraday's constant is 96,500. That should look very familiar. The unit we're going to use is joules per volts times mole. And then we're going to have our voltage, which is 3.05 volts. And we're just going to multiply those together. And let me get my calculator because I don't have this written down. -2 times 96,500 times 3.05. Get a really large number as 588,650. If we'll look at some units canceling, volts is going to cancel. You're going to be left with a joule per mole. But Gibbs is actually measured in kilojoules, and so you actually have to divide this answer by 1,000. So you're going to end up getting, if we do 3 sig digs, because I'm kind of fond of 3 sig digs, you're going to get a negative 589 kilojoules per mole of free energy. Negative means it's spontaneous. So, two things can tell us it's spontaneous: a negative G or a positive voltage. And the reason that works is because there's a negative sign hanging out here. So if this had been negative and non-spontaneous, the negative and the negative would have made a positive, and Gibbs would have been positive. So Gibbs and voltage are like opposite as far as sign, as far as spontaneity is concerned. And that is your full lesson. There is one of these on the worksheet. There'll probably be just one of these on the test. It's not that hard. I figure since we were going ahead and using Faraday's constant with those other problems, we were already calculating voltage. All we needed to add was to figure out the number of electrons. And we have to remember to divide by 1,000 just because of the unit difference. A lot of books might use, they divide by 1,000 here. They use 96.5 kilojoules per mole Kelvin, but really Faraday's constant is 96,500. So, and that's what we use for 1 mole of electrons. So it works just to go ahead and do it there and divide by 1,000 at the end. And that is the full lesson, and I would hope you would try to do the worksheet. And if you have questions, you will come in. Your homework is due next class, and there is a test next class. And if you're a BE Day student, your lab is also due on Friday. If you're an A-Day student, you're working ahead, and your lab is actually due tomorrow. So, thank you so much, and hopefully this will help, especially if you were absent. And somehow I'm going to end the show.